For as long as humanity has watched the heavens, Venus has been the brightest and most beguiling object in the night sky. Its light is steady, golden white, unblinking, so radiant that ancient astronomers called it both the morning star and the evening star, a celestial mirror to the sun's own glory. Through early telescopes, it appeared almost flawless, a smooth, luminous disk without blemish or shadow. Where Mars and the Moon revealed craters and contrast, Venus gave nothing. It was a world without features, forever veiled in cloud. For centuries, that mystery endured. Some imagined a paradise, oceans, jungles, even civilizations basking under a permanent dawn. Others suspected a desert beneath endless storms. When the space age dawned, Venus became the first planetary target for both Soviet and American probes. Between 1961 and 1978, a fleet of spacecraft, Mariner 2, Mariner 5, Mariner 10, and the Soviet Venera series, dared to look beneath the clouds. What they found was not paradise, but a planetary inferno. Mariner 2, launched in 1962, made history as the first successful interplanetary mission. It revealed that Venus's surface temperature exceeded 400 degrees Celsius, and its atmosphere was almost pure carbon dioxide. Pressure at the surface was 90 times that of Earth, equivalent to being nearly a kilometer underwater. Later, Soviet Venera landers, engineered like miniature submarines, confirmed the nightmare. The surface glowed dimly through yellow haze littered with angular rocks, under skies so dense that sunlight scattered like a twilight fog. Most landers lasted only minutes before melting or crushing under the weight of the air. Yet despite these grim discoveries, the mystery deepened. What was hidden beneath those sulfuric clouds? Was Venus geologically dead, or did its heat hint at a restless planet beneath? The only way to know was to see through the veil. And for that, NASA would need to turn to radar. Radio waves could penetrate the cloud cover that visible light could not. In 1978, the Pioneer Venus orbiter used radar altimetry to sketch the first crude maps of Venus's surface. The results astonished scientists. Mountain ranges, vast plains, and enormous highlands rose from the gloom. The planet was not a uniform wasteland, but a varied landscape of ridges and basins. Pioneer's radar glimpsed two continents, Aphrodite Terra, sprawling near the equator, and Ishtar Terra, crowned by Maxwell Montes, the tallest peak on Venus. But the resolution was coarse, the details blurred. The tantalizing truth still lay hidden in the haze. A decade later, NASA launched the mission that would finally lift the veil. Its name was Magellan, a tribute to the explorer who first circumnavigated Earth. Launched in May 1989 aboard the Space Shuttle Atlantis, Magellan was a marvel of precision. A synthetic aperture radar orbiter designed to map nearly 98% of Venus's surface with unprecedented clarity. It would orbit in the opposite direction of the planet's slow rotation, gathering radar echoes to build a global mosaic finer than any map of Earth's ocean floors. When Magellan reached Venus in August 1990, the planet appeared deceptively serene, a featureless sphere shrouded in pearly cloud. But beneath that calm exterior, the radar pulses began to return a world forged in fire. The first images stunned the mission team: volcanoes, fissures, lava plains, and immense coronae. Circular structures hundreds of kilometers across formed by upwelling magma. The planet's surface gleamed in radar images as though dusted with metal. What emerged was a world of overwhelming geological youth and violence. Venus's plains were not ancient like the Moon's or Mars's. They were smooth and uncratered, suggesting that the entire surface had been resurfaced in a planetary cataclysm only a few 100 million years ago. Whether by massive global volcanism or a series of titanic mantle eruptions, the crust had been melted and renewed in a geologic heartbeat. Magellan revealed that craters were scarce and randomly distributed, implying that the surface was young on a cosmic timescale, perhaps less than 500 million years old. Venus, it seemed, had erased its own history. The imagery showed towering shield volcanoes rivaling those of Mars. Mat Mons, rising 8 kilometers high, dominates a region of cracked lava plains the size of Europe. Radar reflections indicated flows extending for hundreds of kilometers, some fresh enough to suggest relatively recent activity. There were channels resembling river valleys, but carved not by water, rather by liquid rock. Some stretched for thousands of kilometers, the longest known lava channels in the solar system. Magellan's radar also uncovered a network of fractures and tesserae, intricate tile-like terrains of ridges and troughs twisted by immense tectonic forces. Unlike Earth, Venus shows no sign of plate tectonics. Its crust is a continuous shell, but it is far from static. The planet seems to have suffered massive episodes of crustal overturn, where the heat trapped beneath its thick mantle burst outward, ripping the surface apart and resurfacing the globe. Each event may have unleashed enough gas to reshape the atmosphere itself, a recurring cycle of burial and rebirth beneath the clouds. The radar altimeter painted a dramatic portrait of elevation. Vast plains, Atalanta planitia, Guinevere planitia, and Lavinia planitia lie at the lowlands, while Ishtar Terra rises like a high plateau. At its summit stands Maxwell Montes, reaching 11 kilometers above the mean surface, higher than Mount Everest. Bright radar echoes near its peaks suggest metallic frost, possibly pyrite, the mineral known as fool's gold, condensing out of the dense atmosphere. On Venus, even the mountaintops glitter with poison. Magellan's data revealed thousands of volcanic edifices, from massive shields to tiny domes only a few kilometers across. Some clustered in fields, others formed long chains along fractures. Among the most striking were the coronae, circular formations up to 2,000 kilometers wide, ringed by ridges and fractures. Scientists believe they mark regions where mantle plumes rose, domed the crust, then collapsed. These coronae are unlike anything on Earth, a signature of Venus's unique internal dynamics. The planet, lacking Earth's ability to relieve heat through plate motion, may instead vent its energy through catastrophic episodic volcanism. As the mission continued through the early 1990s, Magellan transmitted nearly 30 terabytes of radar data, mapping the planet with a resolution of 100 to 200 meters per pixel. From that data, scientists reconstructed a geological story of contrasts, at once alien and familiar. Beneath the suffocating clouds, the terrain is hauntingly Earth-like. Mountain belts, volcano chains, fractures, and plains that resemble flood basalts. Yet, everywhere, the scale is amplified, exaggerated by pressure and heat. The radar brightness changes with slope and roughness, giving Venus's landscapes an eerie three-dimensional glow. In some images, ridges and craters gleam like bones beneath skin. Magellan's radar also detected subtle changes in the returned echoes over time, tiny variations that hinted at surface deformation or lava flows occurring during the mission. If true, it would mean that Venus is not just recently resurfaced, but potentially active today. Later observations from Earth-based radar systems would reinforce this idea. Certain volcanic regions, including Mat Mons, appear to have changed brightness over decades, consistent with new lava deposits. Through these revelations, Venus's image transformed from a lifeless twin into a dynamic, dangerous planet. Its deceptive similarity to Earth, in size, mass, and density, conceals an entirely different fate, Where Earth's carbon became sequestered in oceans and limestone, Venus's carbon dioxide remained trapped in its atmosphere, creating a runaway greenhouse that turned oceans into vapor and rocks into embers. The Magellan mission did more than map a surface. It laid bare the consequences of atmospheric evolution gone astray. Yet amid the scientific rigor, there was also awe. To planetary geologists, the radar mosaics were like paintings of a world that should not exist. A place of endless dawn, bathed in yellow light, where the ground glows red with heat, and thunder rumbles in a sky of sulfuric acid. In these images, Venus became mythic again, a world that mirrored humanity's fascination with beauty and destruction. It was the goddess and the inferno, the brightest star and the deepest warning. By 1994, Magellan's primary mission was complete. The spacecraft, having orbited Venus more than 15,000 times, was commanded to plunge into the atmosphere. It burned up silently on October 13, 1994, vanishing into the eternal clouds it had unveiled. Its final radar maps remain among NASA's greatest cartographic achievements, a complete global atlas of a world once thought unknowable. In the decades since, Magellan's data has been reprocessed with modern algorithms, revealing finer details than its engineers ever imagined. Hidden in those archives are clues to ongoing volcanic and tectonic activity, to the formation of mysterious radar-bright patches that may shift with time. Venus is no longer viewed as static, but as a living planet caught in perpetual fever. Magellan's success also reshaped our ambitions. It proved that radar could pierce the thickest atmospheres and illuminate the most inaccessible worlds. It prepared the path for future missions, NASA's Veritas and Da Vinci, ESA's Envision. To return to Venus with new eyes and instruments. Together they will attempt to answer the question that has haunted every scientist since Magellan's last transmission. Is Venus still alive? As we look back, the irony is profound. The planet that once symbolized beauty turned out to be a mirror of our own potential ruin. Beneath its flawless glow lies a cautionary tale written in basalt and cloud, a reminder that even twin worlds can follow diverging destinies. The veil has been lifted, but the mystery only deepens. Fire beneath the mist, volcanism, atmosphere, and runaway greenhouse. The world beneath Venus's radiant clouds is a place of unbearable tension, a planet where heat and pressure conspire to erase every boundary between rock, air, and fire. Its skies swirl with sulfuric acid droplets, its winds scream at hurricane speeds, and its surface glows dimly under a perpetual orange twilight. At 470 degrees Celsius, Venus is hotter than Mercury, even though it lies nearly twice as far from the Sun. This paradox defines its character. Where Mercury is seared by proximity, Venus burns by its own making. To understand why, we must first step through its suffocating atmosphere. The air of Venus is composed of 96.5% carbon dioxide, 3.5% nitrogen, and traces of sulfur dioxide, water vapor, and hydrochloric acid. It is a greenhouse gone wild, the densest, most toxic shroud of gases ever measured on a rocky planet. The result is a crushing surface pressure of 92 bars, equal to that at 900 meters below Earth's oceans. A human standing there would be flattened and boiled within seconds. High above, at altitudes of 50 to 70 kilometers, the story changes. There, temperatures are temperate, around 20 degrees Celsius, and the air, though still acidic, is thin enough to float a balloon. But descend below the cloud decks, and each kilometer adds another 10 degrees to the heat. Sunlight filtered through thick haze becomes a dim glow. Shadows fade, and even the horizon bends in refraction. The clouds act like mirrors, scattering light until day and night are almost indistinguishable. To machines that have landed there, Venera, Vega, and the Pioneer Venus probes, the surface appears like a world under molten glass, the sky glowing sulfur yellow and the air shimmering with heat. The reason for this inferno lies in a runaway greenhouse effect, one of the most extreme climate transformations known in the cosmos. Billions of years ago, Venus may have had oceans, rain, and mild weather. The sun, fainter then, warmed it gently. But as solar luminosity increased, Venus's surface warmed just enough to release more water vapor into the atmosphere, a potent greenhouse gas. That vapor trapped more heat, which in turn released even more water. The cycle fed on itself, accelerating into catastrophe. Eventually, the oceans boiled away. Water molecules in the upper atmosphere were split by ultraviolet light, and the liberated hydrogen escaped into space. With its water gone, Venus lost its ability to regulate carbon dioxide through the rock-weathering cycle that stabilizes Earth's climate. Volcanic outgassing filled the sky with carbon dioxide and sulfur compounds, which the planet could no longer recycle. The result was permanent atmospheric lockdown, a climate apocalypse that sealed Venus's fate. NASA's Pioneer Venus mission in 1978 was the first to truly explore that atmospheric hell. Its entry probes parachuted through the clouds, measuring pressure, temperature, and chemical composition at every level. The results astonished scientists. The atmosphere was not a simple blanket, but a dynamic, multi-layered system, alive with chemistry and motion. Sulfuric acid droplets condensed at mid-altitudes, forming dense, reflective clouds that give Venus its brilliant shine. Above them, ultraviolet light sculpted streaks and waves across the planet, driven by high-altitude winds that race around the globe in only 4 days. Superrotation, where the atmosphere spins 60 times faster than the planet itself. The lower layers, however, are lethally still. Down near the surface, the air is almost motionless, a heavy sea of heat and pressure. It is here that volcanic gases accumulate, feeding the greenhouse engine. Data from orbiting missions show that the atmosphere is not static. Concentrations of sulfur dioxide fluctuate dramatically over time, a sign that active volcanoes may still be venting from below. Venus's volcanic nature is legendary. Magellan revealed more volcanoes than any other planet, over 1,600 major structures, and perhaps hundreds of thousands of smaller vents. Some regions are coated in smooth plains of basaltic lava that stretch for hundreds of kilometers. In radar images, they resemble frozen oceans of fire. The composition of these rocks, inferred from Venera lander analyses, is similar to basalt on Earth. Evidence that the planet's interior remains hot and convective, its mantle still capable of melting and erupting. But on Venus, eruptions are unlike anything we know. The air is so dense that lava cools more slowly and plumes cannot rise far. Explosive eruptions are muted. Instead, lava oozes across the plains, forming broad shields and channels. Some of these flows have reflective surfaces in radar imagery, suggesting they are geologically young, perhaps only a few million years old. In planetary terms, that is yesterday. Supporting this picture are observations of lightning detected by the Pioneer Venus orbiter and later confirmed by European missions. Flashes illuminate the clouds at night, accompanied by bursts of radio energy. On Earth, lightning implies atmospheric convection and charge separation. On Venus, it likely occurs in the sulfuric acid clouds or near volcanic plumes where ash particles collide. In either case, it reveals a restless electrical world, a planet whose storms whisper of continuing activity. The atmosphere's strange chemistry is equally mesmerizing. At the top of the clouds, sunlight breaks apart carbon dioxide and sulfur compounds, producing a mysterious yellow haze of unknown absorbers that darken certain regions in ultraviolet light. These patterns shift with wind currents, giving Venus its streaked, banded appearance. For decades, scientists have tried to identify the culprit. Candidates include iron chloride, sulfur allotropes, or even microbial pigments. Whatever the cause, it demonstrates that Venus's climate is a perpetual experiment in atmospheric transformation, where sunlight, chemistry, and heat collaborate in chaotic equilibrium. Beneath those clouds, the surface pressure acts like a lid on the planet's geology. Without plate tectonics to vent heat, Venus may experience periodic outbursts, planetary resurfacing events that melt vast regions at once. Some models suggest that every half-billion years, the crust softens under trapped heat, ruptures, and floods the globe with lava, erasing old terrain. The young surface age revealed by Magellan supports this theory. If so, Venus's geology is cyclical, quiet for eons, then cataclysmic beyond measure. The deeper question is how this infernal planet diverged so violently from its twin, Earth. Both worlds share nearly the same mass, radius, and bulk composition. Both likely began with oceans and atmospheres rich in carbon dioxide and water vapor. Yet Earth cooled, condensed its water, and developed life, while Venus spiraled into fire. The difference may lie in distance, a mere 30% closer to the Sun, but also in chance. Small variations in early rotation, volcanic timing, or atmospheric loss may have tipped Venus over the edge. In that delicate balance, we glimpse the razor's edge on which habitability itself depends. NASA's observations also hint that Venus's climate is not entirely static even now. The sulfur dioxide levels measured by Pioneer Venus were far higher than those seen by later missions, implying that some great eruption had injected gas into the upper atmosphere shortly before the spacecraft's arrival. Decades later, European and Japanese orbiters recorded similar fluctuations. If these signals truly originate from volcanism, Venus is still breathing, exhaling its interior into the sky. The concept of a living planet, not biologically but geologically alive, transforms Venus from a symbol of death into a dynamic system. Its volcanoes may replenish the clouds that hide them. Its winds may carry sulfur from deep vents into the high atmosphere. Its lightning may forge new molecules in the dark. Even the temperature, though stable for eons, reveals subtle gradients that scientists use to trace circulation cells, like atmospheric rivers. Venus, far from being a stagnant wasteland, is a planet in slow, eternal motion. Yet for all its violence, Venus also speaks to our future. Its runaway greenhouse effect serves as the starkest possible warning to Earth, an example of how fragile climate equilibrium can be. If carbon dioxide accumulates unchecked, oceans boil, and cooling feedbacks fail, any temperate planet can cross the same irreversible threshold. Venus is not just a twin, it is a prophecy, written in heat and pressure. Modern climate scientists study Venus's radiative balance to refine models of Earth's own atmosphere. The lessons are unsettling. Once the tipping point is passed, recovery may be impossible for billions of years. The dense CO2 blanket acts like an eternal memory, trapping the ghost of every eruption, every molecule that once belonged to an ocean. When the Pioneer and Venera probes descended through the clouds, their final transmissions were surreal. The air temperature rose past 300 degrees Celsius, 400 degrees Celsius, 450 degrees Celsius. Then, the instruments failed. Pressure gauges shattered, lenses fogged, circuits melted. In those last moments before silence, the cameras glimpsed angular stones scattered on the reddish plain, faintly illuminated by sunlight filtered through sulfur. No wind stirred, no sound could carry, just heat and time. From orbit, Magellan continued to map that hellish surface, proving that the very mountains shimmer with metallic minerals and the valleys still bear the scars of ancient flows. Lightning still flickers through the haze. Sulfur still cycles through its phases, condensing and evaporating in endless loops. And somewhere beneath that crust, the mantle still churns, releasing the slow heartbeat of a planet that once might have been a second Earth. Venus, in the end, is not a failure of creation, but an extreme of it, a laboratory of planetary destiny. It shows us that the same forces that made Earth habitable can just as easily unmake it. Beneath its veil of clouds lies the record of that transformation, frozen in basalt and gas. To study Venus is to peer into the mirror of planetary evolution and see our reflection dimly in the heat. And yet, high above that inferno, 50 kilometers above the surface, there floats a narrow layer of calm. Temperatures Earth-like, pressures tolerable. There, amid sulfuric acid clouds and carbon dioxide haze, some faint chemistry stirs that defies easy explanation. It is toward that tenuous hope in the final section of this chapter that the story now turns. Life in the clouds, the Phosphine controversy, and future Da Vinci/Veritas missions. For more than half a century, Venus has stood as a symbol of finality, a world where life, if it ever began, was long extinguished by fire. Its clouds, dense with sulfuric acid, seemed the least likely refuge for anything living. Yet in September 2020, a quiet announcement from an international team of astronomers sent a shockwave through the scientific world. Using radio telescopes in Hawaii and Chile, they had detected a faint but unmistakable spectral fingerprint. Phosphine gas, pH3, drifting in the Venusian atmosphere at altitudes where conditions are surprisingly mild. On Earth, phosphine is produced almost exclusively by life, by microbes, decaying organic matter, or human industry. Could it be that the most hostile planet in the solar system harbored signs of biology in its clouds? The discovery, if real, would rewrite everything we thought we knew about Venus. Phosphine should not exist there. In such a strongly oxidizing atmosphere, the gas ought to be destroyed within hours. No known geological or chemical process can produce it in measurable quantities under Venusian conditions. Its presence implied either unknown chemistry or something far more radical. Life persisting in a layer of the atmosphere 50 kilometers above the inferno, where pressure and temperature mirror those of Earth's lower troposphere. The announcement ignited a frenzy. Some hailed it as the most important astrobiological clue since the discovery of Martian organics. Others urged caution. Within months, teams around the world re-examined the data. Critics argued that the spectral lines could have been misinterpreted, that what was seen might be sulfur dioxide, SO2, not phosphine. Subsequent observations with the same telescopes yielded conflicting results. The signal appeared weaker, perhaps vanishing entirely. Yet the debate refused to die. The idea that something unexplained was happening in Venus's clouds remained stubbornly alive. To understand why the claim resonated so deeply, one must consider Venus's unique vertical environment. Beneath the clouds, the atmosphere is a furnace, but above them lies a region that is, astonishingly, temperate. Between 48 and 60 kilometers altitude, temperatures range from 20 to 60 degrees Celsius, and the pressure is roughly 1 atmosphere, almost identical to conditions at Earth's surface. It is a layer of perpetual twilight, illuminated by sunlight filtered through sulfuric mist. If anywhere on Venus could host life, this is it. In this habitable zone, acid droplets float like tiny laboratories. Inside them, complex chemical reactions occur, interactions between sulfur, carbon dioxide, and trace water vapor. Some models suggest that within each droplet, microenvironments could exist with enough neutralization to sustain exotic chemistry. The notion of aerial microbes drifting endlessly in these clouds is not new. As early as the 1960s, Carl Sagan and Harold Morowitz proposed that microbial life might have retreated into the atmosphere when the surface became uninhabitable. Instead of oceans, Life would ride the winds, feeding on sunlight and chemical gradients. The 2020 phosphine detection breathed new life into that daring idea. The gas itself is a fascinating clue. On Earth, phosphine forms in anaerobic environments, swamps, sewage, and the intestines of certain bacteria, where phosphorus compounds are reduced by biological metabolism. It is also manufactured industrially, but rarely through abiotic processes. To produce it naturally on Venus, one would need either lightning-induced reactions of phosphides, which the planet lacks, or high-temperature chemistry deep in the mantle, somehow venting into the upper atmosphere. No plausible volcanic pathway can generate enough phosphine at the observed concentration. And yet, the signal was there, faint but persistent. NASA's orbiters had not been designed to search for such chemistry, so the detection came from Earth-based radio observations. Follow-up studies using archival data from the Pioneer Venus mission found hints of related phosphorus compounds in the same atmospheric layers, though not conclusively. Others reanalyzed the line profiles and concluded that even if phosphine exists, its abundance might be much lower than first reported. But whether the signal was artifact or reality, it accomplished something profound. It refocused the world's attention on Venus. Within a year, NASA announced 2 new missions to revisit the planet, the first in 3 decades. The first, Da Vinci, deep atmosphere Venus investigation of noble gases, chemistry, and imaging, would plunge directly through the clouds, sampling their gases and measuring isotopes of argon, neon, and xenon to trace the planet's history. The second, Veritas, Venus emissivity, radioscience, INSAIR, topography, and spectroscopy, would orbit and map the surface in exquisite detail, searching for signs of active volcanism and tectonic movement. Together, these missions represent a renaissance in Venus exploration, spurred in part by the phosphine controversy. Da Vinci's design is audacious. Its descent sphere, encased in thermal armor, will fall through the atmosphere like a scientific meteor, transmitting data for about an hour before succumbing to the heat. Along the way, it will sniff for phosphine, sulfuric aerosols, and other potential biosignatures while photographing the terrain of Alpha Regio, a tessera plateau that may preserve Venus's oldest rocks. Veritas, meanwhile, will use synthetic aperture radar to remap the entire planet at 30-meter resolution, improving on Magellan's legacy and searching for surface changes that betray volcanic eruptions in progress. If active volcanoes are found venting gases into the sky, they might provide the missing explanation for phosphine, or eliminate the biological hypothesis altogether. ESA's Envision mission, launching later in the decade, will complement NASA's pair with deep subsurface radar sounding, probing the crust for buried structures and reservoirs. Together, these 3 missions mark a new era, a concerted effort to understand why Venus evolved so differently from Earth, and whether some shadow of habitability lingers still. Beyond their scientific goals, they carry a human message that exploration does not end when a world disappoints our expectations. For decades, Venus was dismissed as unworthy, too hot, too hostile. Now it stands once more at the forefront of inquiry, its clouds the subject of renewed fascination. As debate over phosphine continues, alternative explanations multiply. Some researchers suggest that the gas could arise from photochemical reactions not yet modeled, interactions between sulfur dioxide, chlorine, and solar radiation that might produce transient phosphine-like spectra. Others posit electrochemical processes in cloud droplets or reactions on the surfaces of mineral aerosols. None fully account for the observations, but each brings us closer to understanding the strange chemistry of this planet's skies. The truth may not be biological at all, yet even if it isn't, the search itself expands the frontier of planetary science. And what if, against all odds, life truly does linger there? What form could it take? Imaginations run wild. Microbial cells coated in sulfur polymers to resist acid, using ultraviolet light to power exotic metabolisms. These beings would not walk or crawl, but drift, suspended in cloud droplets, dividing slowly as they rise and fall with the winds. Their world would be one of endless sunlight filtered through amber haze, an aerial ocean without a surface. If such life exists, it would represent an entirely new evolutionary niche, a second genesis of biology in our solar system. Philosophically, the possibility carries weight. Venus, once thought to embody fertility and beauty, became our cautionary tale, the lost twin consumed by its own greenhouse. To find life there, even microscopic, would be to restore balance to that myth. It would suggest that life is not fragile, but persistent, capable of adapting even to acid and fire. From the perspective of astrobiology, Venus also serves as a crucial laboratory for understanding exovenuses, the many Earth-sized planets discovered orbiting close to other stars. The James Webb Space Telescope has already begun probing the atmospheres of such worlds, looking for combinations of gases that signal disequilibrium, oxygen, methane, or phosphine analogs. By decoding Venus's chemistry, NASA can better interpret the spectra of distant exoplanets and distinguish between living and lifeless skies. The search for life in Venus's clouds may thus help identify life among the stars. In a sense, Venus has always been our mirror. It shows us how small changes in distance, pressure, and chemistry can steer destiny. The same elements that sustain us, carbon, oxygen, sulfur, also conspire to destroy us if balance falters. In the phosphine signal, whether genuine or illusory, we glimpse a metaphor as powerful as the data itself, that even amid ruin, curiosity endures. When Da Vinci and Veritas finally arrive in the early 2030s, the moment of truth will come. The descent probe will pierce the clouds, its sensors alive to every molecule, its cameras glimpsing the hidden surface through gaps in the haze. The orbiter will sweep overhead, mapping the landscape with laser precision. If phosphine is found again, if it lingers stubbornly in that middle layer where temperature and pressure invite speculation, the mystery will deepen beyond imagination. If it is absent, Venus will still have spoken, revealing not disappointment but understanding, a world remade, its chemistry a reflection of cosmic possibility. Either way, the lesson of Venus will endure. It reminds us that life's potential is not confined to comfort, that the same physics which create hell may also permit adaptation. From the scorched plains below to the cool twilight above, Venus embodies the full spectrum of what a planet can become. In the end, perhaps that is the true gift of the phosphine controversy. Not the promise of aliens in the clouds, but the rekindling of wonder for a world we once abandoned. Venus, the brightest planet, has reclaimed her role as both mystery and mirror. Through her shroud of cloud and acid, she whispers to us still, "Look closer, for the familiar and the unimaginable may share the same sky."